Today the topic of this lecture is helical compression spring. Actually in this problem we have two springs. If you see over here, this is the top view of one spring and this is the top view of another spring. This is the bigger spring and this one is the spring that have small mean coil diameter, which is this one. So in this problem we have two concentric helical compression springs and one spring that is smaller and mean coil diameter is inserted into the another spring, and after that it is forced by an amount of 3 kilonewton. Both the springs are made up of steels, and when they are loaded and unloaded they have the same length. Means that when they are loaded the deflection in both the springs will be equal to each other. So y1 will be equal to y2, and since it is loaded with 3 kilonewton, so in these 3 kilonewton some of the force will be taken by this spring that have small mean coil diameter, and some of the force will be taken by this spring that have large mean coil diameter. So F1 plus F2 is equal to 3 kilonewton, and as you know that F is equal to Ky, since the deflection y1 and y2 are equal to each other, so F1 is equal to K1y and F2 is equal to K2y. And if you rearrange this equation, y is equal to F1 divided by K1 and y is equal to F2 by K2. As you know that K is also equal to wire diameter to the power 4 into G divided by 8 into mean coil diameter cube into Na. The value of wire diameter, mean coil diameter and Na are given, but the value of G is not known. The value of G can be found from the table, but till now we don't need to find the value of G. For the first spring the value of mean coil diameter is 45 and wire diameter is 8 millimeter and number of active coils are 5. So putting these values, it will give you 0.001124 G millimeter. So this will be the value of K1, and similarly if you want to find out the value of K2, what you will have to do is to put the value of mean coil diameter to be equal to 25 millimeter and wire diameter to be equal to 5 millimeter and number of active coils to be equal to 10. So when you put ththese values, it will give you K2 is equal to 0.0005 G millimeter. Now since you know the value of K2 and K1, these values can be put over here in this equation. You will get this. So y is equal to F1 by K1, which is equal to F1 by 0.001124 G, and similarly y is equal to F2 by K2, which is equal to F2 by 0.0005 into G. So you can equalize these two to each other. After equalizing these two with each other, then G will be cancelled out with each other, and you will get F1 divided by 0.001124 equals to F2 divided by 0.0005. Rearranging this formula for F1, that will give you F1 equals to F2 divided by 0.0005 into 0.001124. So after the calculation, F1 will be equal to 2.248 into F2. Now if you put F1 to be equal to this in this equation, so 2.248 F2 plus F2 equals to 3 kilonewton, and after adding 2.248 with 1, it will give you 3.248 F2 equals to 3 kilonewton. So F2 will be equal to 0.924 kilonewton, and if you put this value over here in this equation or in this equation, it will give you F1 equals to 2.076 kilonewton. So as y equals to F1 divided by K1 and F1 is equal to 2.076 and K1 is 0.001124 G, or it is also equal to F2 by K2, which is equal to 0.924 divided by 0.0005 G millimeter cube. As you know that you can find out the value of G from this table. In the problem you are given that the spring is made up of steel, and this music wire is steel, this hard drawn wire is steel, this is steel. In fact all of them are steel. So you can take any type from this table, but here I have taken the value of G from the net. I will take a structural steel and the value of G for it is 79.3 gigapascal. So I will take this value and put it over here or over here. So I'm taking this one. Instead of kilo you will have to write 10 raised to the power 3, and instead of this millimeter you will have to put 10 raised to the power minus 3 meter. So this is for the kilo, and this is for the millimeter, and this 10 raised to the power 9 as for this giga. In fact, I'm going to write the units with it. This is meter and Pascal, and as Pascal is equal to Newton per meter square, so put Newton per meter square over here. This meter and this meter square will get cancelled out with each other. It will give you meter, and this Newton will get cancelled with this, so you will get 1 over meter. This meter will come over here to the denominator, and after the calculation of this you will get 0.019 meter, so it is equal to 19 millimeter. So this will be the deflection and the spring which was required in the problem. And after that you are required to find out the stresses in the spring as well, as tau 1 is the stress produced in bigger spring, so it is equal to kb into 8f1 mean coil diameter divided by pi into wire diameter cube, and kb is equal to 4c plus 2 divided by 4c minus 3, and c is equal to mean coil diameter divided by wire diameter. As you know that mean coil diameter is 45 and wire diameter is 8, so putting these values it will give you 5.625. Similarly, f1 is calculated to be equal to 2.076, and mean coil diameter is 45, wire diameter is 8, and kb is 4c plus 2 divided by 4c minus 3. So putting these values it will give you 583.8 megapascal. Similarly, the stress in the second spring will be equal to kb into 8f2 into mean coil diameter divided by pi into wire diameter cube, and kb is equal to 4c plus 2 divided by 4c minus 3, and c is equal to mean coil diameter divided by wire diameter. As you know that mean coil diameter is 25 and wire diameter is 5, so when you put these values it will give you c to be equal to 5. So I have put c to be equal to 5, and similarly f2 is equal to 0.924, and this is mean coil diameter and this is wire diameter, so when you put these values it will give you 609 megapascal. This is the stress produced in the one spring, and this is the stress produced in the second spring, and this is the deflection in both the springs.